Welcome to the sixth problem solving session in the hot track. I will start sharing my screen now. Oh, sorry, Zoom isn't letting me select the window that I want. There we go. Now the chat is gone. Okay. Okay, here we go. Today's problems are, well, about yesterday's lecture, and we talked about contractibility and fibers. So contractibility is a very important concept. It's contractible types are, in a sense, the most simple ones because they have only one element up to homotopy, and we actually know that they have an element. And in this case, we want to prove that the empty type is not contractible, and the idea is, of course, to use that contractibility means that the empty type has an element. So to prove this, we simply write down the definition of is contractible, the empty type. What does it mean? That means we have an element C in the empty type together with a map, proving that for X in the empty type, C is equal to X in the empty type. And this has a first projection map to the empty type, to the first component of the sigma type here. And so since this is inhabited by assumption, then that would imply that the empty type is inhabited, and that's a contradiction. Moving on, another exercise about observational equality. I'm pretty confident that this is the last one. But here we're asked to prove that the observational equality of any n with the successor is empty, and that's also pretty straightforward. We simply prove this by induction on the natural numbers. So for n equals to 0, we have the EQ. I dropped the n, the bold n, because there is only one type we're talking about here, of 0, and the successor of 0, so 1. This is by definition the empty type, this clause. This is empty. And we can, by induction, also prove that for suck and the observational equality of the successor of n and n plus 2, that's by definition just that's this clause, the observational equality of n and n plus 1, and by induction hypothesis, this is the empty type. But here the equality is not judgmental anymore. Okay, so that's not surprising. By the way, if you have any questions, feel free to unmute yourself if that's more comfortable than asking in chat. Okay, so we've pretty much established an equivalence of the observational equality and the identity type of the natural numbers. And such an equivalence should really exist for us to be able to call this observational equality. And now we want to prove that the natural numbers are uncontractible. And I also hope that's true, because the natural numbers is a set with infinitely many elements. So in particular, it shouldn't have only one element. So so to prove this, we assume that suppose we had a proof, a witness that n is contractible, with center C and contraction phi. Let's write that down. It is contractible n, and that's by definition a natural number C, and a witness that for all x and n, C is equal to x. And given this type, we can simply apply phi to the successor of n. And what is phi at the successor of n? It's a proof that that's a proof that C is equal to C plus 1. Yeah, so suck C to be consistent. But we have an implication here. Actually, we have an equivalence, but that's not needed here. We have an implication here, a function to the equality on the natural numbers between C and Zuck Z, and we just proved above that this is equal to the empty type, and this equality also gives us a function. And so the composition of this really implies that this element gives us an element of the empty type. So our assumption that we have such a C and a phi has to be disregarded. No questions so far. First exercises are pretty simple indeed. Now we are asked to prove in the third exercise that if any type is contractible, then its identity type is also contractible. And this just means that if we have a type at the bottom level, which simply consists of one point, and you can reach everything continuously by a path, then those paths aren't more complex themselves. There's really just one way. There are no more non-trivial homotopies in the levels above. And there is a million ways to prove this. So one way is, if A is contractible, to show that straightforward to give for every path a center of contraction, and also the contraction itself. We could also independently prove that every identity type is inhabited, and that the identity types of contractible types are propositions, so that they have at most one element. The path chosen in the solutions is to show that the identity type is equivalent to the unit type. So we assume, again, suppose we have a center of contraction and some contraction phi. And we want to show that for all x and y in A, x equals to y, this identity type in A is equivalent to the unit type. And all right, so let's assume we have some x and y in A. Then there is only one map, x, y, x equal to y to the unit type. That's usually noted by a bang. And that's also const star. And in the other direction, so let's continue here. a map from 1 to x equals y. Yeah, here, okay, so we have here a type family over a contractible type. And one is contractible, that was proved in the lecture, so we're allowed to use singleton induction. Singleton induction allows us to reduce this case to the case where x is judgmentally equal to y. So let's write by singleton induction suffices to give, let's call this map G, from the unit type to x equals x. Well, and in this case, actually, we not only to x equals x, but we have this type family, and we may fix it as at any element of A. So we can even assume that x is judgmentally equal to C, and which is judgmentally equal to y. So it suffices to give an element of C equals C. And yeah, we simply map star to reflexivity of C. So a different way to approach this, if we only had x equals x, is that we can prove that the center of contraction is irrelevant if we have a contractible type. So if this is a center of contraction and we can find paths everywhere, then we could also choose this point. And then a path from this point to here would simply be a composition of this path, which exists because this is a center of contraction, and then composed with that one. And on one side, you have to take the inverse. All right, so we have these inverse maps. And we know that that cons star of G of star is equal to star. And we can prove this, or we can prove this well by a singleton induction or anything, but we a more elegant argument, I would say, is to use that one, the unit type is a proposition, so any two elements of this are equal a priori, and so these elements here have to be equal to 1. Once I have a center of contraction, any element may be chosen for a center. Yes, that's correct. Of course, then you have to adapt your contraction again. But yeah, if you have C and phi, it has to be connected. Yeah, why contractible types are always connected. They have the simplest homotopical structure that you can imagine, and you can think of them as having only one point. So if you choose a hypothetical different one point, so let's say you have this is a witness of contractibility, and then you have some other C prime in A. Then phi of C prime witnesses that C is equal to C prime. So any other point is connected to it by a path. And then we also need to define a contraction for this new center of contraction. And what should phi prime of the third point, C double prime be? Well, that's not the center of the third point, any point x here. Be, well, we have this path and this path. So let's try to concatenate phi of C prime inverse, and then phi of x, right? Phi of so yeah, I mean, yeah, one is truly a singleton. But what's a singleton? A singleton is defined to be an element which satisfies singleton induction. and a type is contractible if and only if it satisfies singleton induction. So you can't really distinguish them, maybe by the induction principle, but in the end it amounts to the same. We have any we have is contractible A, implies A is equivalent to this, and by univalence this implies that A is equal to unit type. So our type theory really can distinguish between those. Yeah, you're welcome. This one thing. Yes. Yeah. It should be possible to construct such a contraction directly. But of course, yeah, at some point you will, well, you have your center of contraction. Yes, try path induction. Yeah, I'd say it's a bit inconvenient. You have this composition of paths here, one going this way and one going this way, and then you turn one around, and then you have to prove that this composition is equal to an arbitrary path. So proving that the identity type is equivalent to the unit type is more elegant in this case, because you don't have to take care of explicit paths here. But after path induction, it should really amount to the same thing. All right. Yeah, okay. So we know that G is a section for the constant map, and we also want to prove that G of const star of any P is equal to P. And here we proceed by path induction. So this is clear, and is this clear? Well, by path induction, if P is reflexivity, then, well, it doesn't really matter. This will always be star. And G of reflexivity, G of star is defined to be reflexivity. And well, we use path induction, so this is also reference. Let's see. Oh yeah, and regarding the previous discussion, we also have that is prop is contractible. So being contractible is a proposition. That means there's really just one way to prove that the type is contractible. Even though there are so many different ideas and ways of approaching this problem, in the end, it won't matter. Okay, if there are no further questions, I'm moving on to the next exercise. Interesting, yeah. Sometimes it's weird, and sometimes it seems trivial. Sometimes I think that a type with only one element should only be able to have one element in one way, and that's of course true. But sometimes it seems like a strong statement. Recall the first projection function from a sigma type here, and we want to show that this first projection is an equivalence if and only if each B of A is contractible. So yeah, let's follow this. Okay, Goodbye, Samuel. So let's start with the first direction. Assume PR1 is equal. So then by our lecture, it's contractible, which means it has contractible fibers. Then we know that for all A in A, it's contractible. The fiber of the first projection at A. Okay, but what's the fiber of the first projection? This is a sigma type consisting of elements by sigma induction. So this consists of elements of the sigma type, but by sigma induction we may split up those pairs again. So we have elements x and y and sigma x and a, b of a, and witnesses that PR1 of x, y is equal to a, but PR1 of x is judgmentally equal, of xy is judgmentally equal to x, so we really just have x equals a here. Okay, and we want to prove that B of A is contractible. So let's first observe that for any A and A, yeah, so we always prove this for a specific A. This will be the same A throughout the exercise, or at least in this direction. And then we also have two elements, B and B prime, and B over A. Then we first have that A, B, and F A is an element of the fiber of the projection. And also, yeah, and also with B prime here. A, B prime, A. Okay, now we know that BA is, well, no, by assumption, we know that this fiber is contractible. So we know that these two are equal. And so we, in the lecture, we also characterized the identity type of sigma types, and this here is a nested sigma type. So in particular, this implies that AB is equal to AB prime. And here, yeah, here we're in the same fiber, A and A. So again, by the characterization of identity types and sigma types, this implies that B is equal to B prime. And we don't need to transport here because we're in the same fiber. Yeah, and so B of A is contractible. Right, because it's certainly inhabited by assumption by assumption that the fibers are contractible, the fibers are inhabited, so in particular such elements exist, and we've shown that for any two arbitrary elements, any two arbitrary elements in that fiber are equal, and yeah, so we didn't prove this directly in the lecture, but a different way of showing that something is contractible is to use that if we have an element of A, well, this A is in this case, yeah, if we have an element of BA and we know that is prop BA, then we know that is contractible BA. So an inhabited proposition is also contractible. Yeah, now we want to show that transport in B is, oh wait, the other direction, of course. I forgot. So okay, we're continuing the other direction here, and then we'll have to find some space for the next part of the exercise. So conversely, suppose we have BA contractible with center CA. Then we define the inverse, an inverse, and it's called Q in this case, from A to the sigma type. And this maps A to, well, what's the obvious choice here? A and the center of contraction at A. And we want to prove that that's an inverse to the projection map. So left and right inverse. And it's a right inverse judgmentally. So I think that's clear. We have PR1 of Q of A. What's Q of A is just this, and PR1 of this pair is judgmentally equal to A. So this is really just A. And that of course also gives us a path. And Q of A, Q of PR1 yeah, by because B of A is assumed to be contractible, and therefore it's a proposition, we may assume that this arbitrary pair A and B is actually of the form A and contraction at A. That's the same argument as above. This contractible fiber over the constant over one element over a single element. Equality here is really just equality in the second component. So we may assume that B is CA. And then it's already clear. So Q, yeah, because PR1 of A and CA is A. So all of this is just A, and Q of A is A and CA by definition. So yeah, this is equal to A comma B if we apply the reverse path again. Okay, and now I really need some space. Let's see if we can get some. So we're giving this map by transport from some fiber of the projection map to B of A, and we're supposed to show that it's an equivalence, and we will prove that its fibers are contractible. So yeah, let's first draw a picture. You've seen this picture before, but I think it doesn't hurt to see it again. We have the type A, and over that we have the type family B, and here we're given a fixed element A and A, and of course this has its fiber BA, so this type is depicted as a line here. And well, for any other X in A, so transport given any X in A and any path P from X to A, then transport along P really just maps elements Y in B of X to some elements in B of A here. And this one is called transport in B over P of the element Y. And well, yeah, so we want to prove, this map is called K in the solutions. And we want to show that K is an equivalence, so show that fiber of K at any B is contractible. And first of all, why should these fibers be inhabited? They should be inhabited because we can simply choose P to be reflexivity here, and X is equal to A, and then transport, and then Y is some element in BA, and we can simply choose Y equal to B, and then transport over reflexivity that does nothing. So transport B over reflexivity will just be B. So by sort of path induction, it's easy to find some center of contraction. And now we are left to show that these fibers are propositions and not more complex. And well, this is a bit technical again. So we are given some we are given any X, Y, and P in the projection fibers of B, and the witness that K maps, we are in total given an element of the fiber of K. So this is an element of the fiber of K. So we have a fiber in the projection map at B, and a witness that K actually maps this to B, and such a witness is of the form Q of type transport in B of B, the element Y is equal to B. And whereby by the characterization of sigma types, of identity types of sigma types, just let's recall that for any such pairs XY and AB, this identity type is equivalent to a path, and well, the path over P. So in our case, transport P P1 equals P, and that's exactly what we have here, such a path and such a P. Yeah, okay. So I see the solution doesn't prove that that it's a proposition, but it proves actually that the pair I described here but didn't write down is a center of contraction. So let's write down the center of contraction again. The center of contraction should be A, B, center of contraction of the fiber should be A, B, and reflexivity at A. Okay, because we know that K of this is transport reflexivity over reflexivity in B of B, and that is just B. So this would be our center of contraction, and we want to show that any such arbitrary element, is equal to this one. Show that that is x, y, p. I'm sorry about the chaos here. X, y, p is equal to a, b, reference. Okay, and this is, we need to construct in a nested sigma type, and so we first need to construct a path in the first component, but that's a sigma type again. But by the characterization of the equality in this sigma type, since we have such a P and such a Q of this type, or we have such an element of this. Okay. This gives us R in XY with this AP. And now we're left to prove that we can lift this to a path of the entire tuple. Yeah, if this is not clear enough, please ask questions. I'm happy to repeat the argument. Okay. Yeah. Now, this is a remark in the lecture, and the remark in the lecture, so you can see this as a lemma, is that if we transport in the fiber, so in the witness that something is a fiber, over some path P, and P is here a witness that A is equal to A prime, or X is equal to A. So this is of type FA equals B to F. Okay, none of this is working here. Fx equals B to Fa equals B. And well, if we have some Q, this gets mapped to applying F to P, inverting, and then composing by Q. And well, we simply prove this by path induction. If B is reflexivity, then this is reflexivity, and then we have the identity map on the fiber. So in particular, we can lift our proof R of the first component of the nested tuple to a proof of equality of the entire tuple by proving that P is equal to applying the first projection to R composed with raffle A. So first is to show. Okay, but yeah, but applying BR1 to R really is just P. So this is judgmentally equal to P, and P composed with vector A is just P. So this is true, and that completes the proof. Yeah. So let's take a step back again. So we have those fibers over the projection, and what we just proved really shows that the fiber of the projection at some fixed element is really just returns you up to a homotopy, the fiber of the type family that you first considered. So this sort of states that fibers and sigma types are well behaved, or viewed differently, that type families are what you expect them to be. Okay, still no further questions. That means I'm moving on to the fifth exercise. That's also an important one. So we have any map F from A to B, and we're supposed to prove that for any such map, we can factor F into an equivalence and a projection map of a sigma type. And so this construction is called the vibrant for me, this seems the way to introduce type families. You mean the fourth exercise or the fifth one? Fourth. Yeah, well, I'm not sure how far type families are introduced here. I mean, we're sort of characterizing fibers over base types. So in a sense, you can view this as a definition of a type over A. But of course, we can't really prove that this, or we can't really get so far and use all of those lemmas without having used type families before. So there's only one way to go here, and that is to first assume a type family B over A, and then hope that the sigma type, or the projection of the sigma type really views, so that we can view, so we have A and we have B, which is sort of a vibration over A, and that sigma A, B, A, that this behaves similarly. Yeah. Okay, so in this case, this has a special name, and it's called vibrant replacement of F. And well, it's a priori not really clear why you need it, but sometimes it's really just helpful to consider this as, well, to factor F, and then you have an equivalence and a projection map, and you know that the projection map behaves well, and you have proved a bunch of stuff about equivalences, so you can use this. But it's also just incarnation of a more general concept. So fiber replacements appear, for example, in displayed categories, or yeah, I guess fiber replacement is just a concept which exists in other areas as well. Okay, enough talking. Let's define E and its inverse. So definition of E. Yeah, what should E of A be? E of A should consist of some element of B. And what's the obvious choice here? Well, let's choose F of A. And then something in the fiber of B, but we already have something in the fiber, and we know that A is in the fiber of B. So let's just take A and reflexivity. Reflexivity at F of A. And an inverse map of an arbitrary y in B and an element of the fiber, let's say X, and witness that this is a fiber. This should be an inverse, so this really has to be X. And defined like this, it's already easy to see that E inverse is a retraction of B, so E inverse of E of A. So this is F of A ref A at FA, and then E inverse projects to this component again, and that's just A. So this is judgmentally equal to A, and from that we get a path. And now, conversely, we want to show that E of of y x p that this is equal to y x p. Okay. Yeah, so we want to prove that those are inverses, and we already know that this computes to just x, and E of x is really, so the whole thing is just fx x raffle and we want to prove now, of course, so we know what this is, and we want to prove that this is equal to the input we gave the composition. So we want to show that this is equal to y xp. And we still have P to be an arbitrary path here, so we may apply path induction. It almost feels like cheating to prove everything by path induction, but that's what it is. So induction on P. Okay, so if we contract P to reflexivity, then we may assume that y is judgmentally equal to fx, and P, well, P is reflexivity. So P is reflexivity, and reflexivity where? Reflexivity at fx. But then the statement is clear already. Yeah, so this will be y, and this is x anyway, and this is P contracted. So that finishes the proof. Yeah, it's almost as simple. Okay, and of course, we still need to construct such a homotopy, witnessing that F is homotopy to the projection after E. But what is the projection of E of X? Well, of E of A. This is by definition just FA, and well, FA is equal to FA, so this trivially commutes. And that's it already. Let's have a look at the time. 8 more minutes. Are there any more questions? Doesn't seem to be the case. In that case, I will stop recording.